Hi, welcome back. In the last video, we saw two properties of systems, which were memoryless and causal. In this video, we're going to look at two more properties, invertible and stability. And before we address these two properties, I do want to point out and emphasize to you that these two properties are not related. Invertibility and stability are not related. I've simply chosen to cover two properties in every video. Okay, let's get started. So, let's talk about invertibility first. Invertibility is important, for example, in lossless coding. If I want to take a file and compress it, and I want to compress it in such a way that I can get back the original data, then I need a compressing scheme that is invertible. So in general, if I have a system here, let's call it S1 for system 1, and I have an input, and I'm just going to call the input X. I'm going to leave off whether this is continuous or discrete, of X of t or X of n, because this, what I'm going to say here, applies for continuous time systems and discrete time systems. And let's suppose the output of this, we can call this whatever we want, we'll call it W. Then, if system 1 is invertible, then if this is the inverse of system 1, then what do you think I get at the output here? I get the output Y is equal to the original input X. Okay, so we can look at this as one big system where the input goes through and then the input, just reaches the output. Nothing's changed. If that's true, then this second system is the inverse of S1 and vice versa. Okay, well, let's start to consider what that really means for us. Now, let's look in continuous time, although this certainly applies to discrete time as well. And let's say, for example, and we'll look at other examples later in the course, that I have a system whose input-output relationship, y of t, is the square of the input signal x of t. Okay? So suppose I had an input signal, we'll just keep it very simple for now. That was kind of like this. Okay, that's it. So maybe this is 2 seconds or something, and this is minus 2 seconds. And I'm going to leave off the height of that on purpose. So if we were to send this input signal through this squaring system, then what we would get out is the following. I would get out, well, let's consider just this first linear piece, the positive side. When I square a line, I get a parabola, right? And then same thing over here, when I square this piece, I get a parabola. So this is what I would expect to get out of such a system. And I want to emphasize invertibility is related to the system. It's a system property. It's not a property about the signals. So my system is the squaring system. I can send whatever I want into the squaring system. For this example, if I send this thing into the squaring system, this is what I would get out of the squaring system. And we want to know, is the squaring system, that's hard to say, squaring system, is the squaring system invertible or not? Okay, well, now let's begin to put some scale to the vertical axis. So let's say that at some certain time, I observe maybe 4, the value 4 at the output. In order to be invertible, then, I need to get back the original signal. So now pretend you do not know what x is, and you just observe y. Can you get back the original signal given y? Well, no, you can't. And the reason you can't is because if you observe, let's say, a 4 in the squaring system, then you don't know if the input at that time was 2 or if it was -2. You don't know. And so this squaring system, with this squaring system, it's impossible to observe the output and get back the original signal, the input. So we would say that this squaring system is not invertible. It's not invertible. And so the definition of invertibility, you can see where we're going here, is that unique inputs produce unique outputs. Unique inputs produce unique outputs. And an input here is the entire signal. Okay, so given this signal, it produces this signal. But I'll give you another signal that produces this signal. Call this g of t. Okay, 2, -2. If I were to put this signal in, g of t, into the squaring system, then, the negatives become positives when you square it, and this also gives me this output. So just by observing this output, I don't know if I got x of t, or if I got g of t, or if I got something different at the input. So in this case, unique inputs, x, g, do not produce unique outputs. They produce the same output. So this is not invertible. Okay? And again, since I'm going to cover another property, I'm just going to label this invertible. Unique inputs produce unique outputs. Okay, so this is just, the squaring system is one example of not being invertible. An example that is invertible is a simple amplifier or a proportional block. So in this case, let's say that the output y of t is twice the input. Okay? So what is the inverse of that? This is invertible. The inverse of this is the following system. So if this is S1, then the inverse, one way of getting the inverse is swapping x with y and then solving for y. And this gives you y of t is equal to 1/2 x of t. So think about that, right, for a second. So if I have system S1 and I plug in x of t, then what I get out is twice x of t. And then when I put that in to the inverse, then I get 1/2, 1/2 what I put in. Well, 1/2 what I put in is 2x of t, so this gives me x of t back. So that's the inverse. Okay, and again, we'll look at other examples in an up-and-coming video. Now, let's look at the second property here, stability. And for stability, this is actually, understanding stability is kind of, it takes 2 steps to understand stability. Then stability, again, is a system property. So these are both system properties. But to understand stability, we first have to understand a signal property. Signal property of boundedness. Okay, so we say the following. A signal x of t is bounded if and only if, so we write if and only if, if and only if a number, or a constant, I guess, a constant b for bound can be found, a finite constant can be found such that the absolute value, or the magnitude of x, is less than b for all t. Okay, so we're not there yet at stability. We're still working on it, but this is step one of figuring out what stability means, figuring out what boundedness means. So a signal is bounded if a finite constant b can be found such that the absolute value of x is less than b for all time. So let's understand what that means. Let's say x was, and I write this in continuous time, but it applies for discrete time as well. Let's suppose that x was a sinusoid, a sine wave. Okay, so sine wave takes on values from -1 to +1. The absolute value of the sine wave then takes on values between 0 and 1. It's no larger than 1. So can I find a b such that this is true? Yes. I can find, how about 1.1? So this signal is bounded by the value 1.1, right? Below and above, the absolute value. And I could choose 1.01, as long as I can just find a b, find a bound to the signal. Okay, so we would say that this signal is bounded. A signal that's not bounded, for example, is 1 over t, right? That signal looks like this. Okay, you cannot find a value for b to kind of squeeze this graph, right? Because this goes to infinity up here, so you cannot find a b to squeeze the graph like we squeezed it over here. So this would not be bounded, not bounded. Okay, so that's bounded. That's a property of signals. Now, to define stability, stability says the following. A system is stable if all bounded inputs produce bounded outputs. Okay? In other words, if I put a signal in that does not go to plus or minus infinity, so we call that, we might say that behaves nicely. If it does not go to plus or minus infinity, then the output should not blow up and go to plus or minus infinity. If I put in a signal that is bounded, and so it does not go to plus and minus infinity, and the output blows up, it goes to infinity, then that's not a stable system. Okay, so I'm going to give you an example of not stable. You might be a musician, or I guess you don't even have to be a musician to know this example. But if you have a microphone, okay, here's my pathetic microphone there. And if this goes to, a PA system, and then that PA system goes to some amplifier, and then goes to a speaker. Okay, this is really a bad drawing, but anyway. And if the microphone is directed such that some of this speaker volume goes back into the microphone, then what you have is a positive feedback loop, right? The sound comes out of the speaker, it goes back into the microphone, that gets amplified, so that gets even louder and louder and louder, and this creates feedback, and this is the thing that hurts all of our ears. So now, if I were to just put in a very small signal, meaning it's bounded, just a little disturbance, nothing too drastic, just a little small disturbance, then that small disturbance goes through the amplifier, it goes through the speakers, right? And then it gets picked up again, so now it's a little bit bigger because it went through the amplifier. It goes through the amplifier again, through the speakers, now it's even bigger. And it keeps going towards infinity, and this thing just blows up. Not literally, of course. There are electronics in place to keep it from blowing up. But the signal gets very loud until the electronics, prohibit it from getting louder. So this sort of system, we would say, is an unstable system. It's not stable. Okay, let's try to quantify that now mathematically with an example. Let's say I have an input-output relationship where the output is 1 divided by the input, maybe minus 1. Okay, and let's say we put in, let's say we put in this signal here. How about that one? So this goes to 0, and then this might be 2. And here's 1. I didn't draw it perfectly symmetrical, but you get the idea. So let's just suppose that I put in this signal. Okay, what would I expect to get out? Well, one over the signal minus 1. So when the input signal approaches 0, the output would approach minus 1. So minus 1 is down here somewhere. So we've got something that's approaching minus 1. Okay. But when the signal approaches 1, this output approaches 1 over 0. Okay, it's actually going to approach minus infinity. It's going to go like this. Something like this. And then when this signal approaches 2, this is going to approach 1. Okay, so this is what the output would look like. And so what you can see is that I have no B. I cannot find a B here to squish this output. Even though I could find a B here to squish the input. I could choose B is equal to 2.1 or something like that. Okay, so in this case, a bounded input produces an unbounded output. So this system with this relationship, input-output relationship, is not stable. Okay, you've got something that goes off into infinity land up here. So remember that if you're going to prove these properties, we said this in the last video, if you're going to prove these properties, if you're going to show that something is invertible, or if you're going to show that something is stable, you have to show that it's true for all inputs, right? You have to show that all unique inputs produce unique outputs for invertibility, and you need to show that all bounded inputs produce bounded outputs for stability. For disproving, then you just have to show one case. So one case where we don't get a unique output, or one bounded input that produces an unbounded output. So in the next video, this can be tricky if you're not used to proving these things, but in the next video, what we're going to look at is how to prove or disprove both invertibility and stability. Okay, so let's take a look.